Today I would like to add a new playlist in my YouTube channel. And actually this new playlist of my channel is General Relativity. It means this playlist will contain the videos on General Theory of Relativity. Definitely you all have heard about this very elegant theory which is called General Theory of Relativity, and you have definitely an idea that this theory was proposed by the famous scientist Albert Einstein after his Special Theory of Relativity. In 1905, Einstein has provided a special theory of relativity, and in 1917 or 1920, this general theory of relativity was proposed by Einstein. Actually, this is the first lecture on this general theory of relativity. Why actually I have started this playlist? The reason is obvious, that it is a very elegant theory, and definitely you all have eagerness to study this general theory of relativity. In fact, I have already provided a playlist of a special theory of relativity in my YouTube channel. And after watching the videos on a special theory of relativity and other videos too, several viewers always request me to provide videos on general relativity. So I have planned actually to provide the videos on general relativity, which will cover the syllabus of almost all universities of India. Actually, this general relativity is taught particularly in M.Sc level in physics and also in mathematics. So, my aim is to cover the whole syllabus of M.Sc level in mathematics and physics for the Indian universities in this playlist. Okay, and this is my first lecture on this general relativity. And since it is my first lecture, so this lecture will only a brief introduction regarding this general relativity. Okay, I would not talk about any basic theory or basic concept of this general relativity, but I will only introduce you why this theory was needed, why its need was felt, okay, and what actually we discuss in this general relativity. These things we will see in this brief introduction. One point you should note here, that actually to understand the concept of general relativity, you must have a concrete knowledge of tensor algebra and tensor calculus, both of these, because every equation of general relativity will be in tensorial form. Why we write equations in tensorial form, we will also learn during these lectures. And so you definitely have a solid knowledge, a concrete knowledge of tensor analysis. You can find some of the videos on this tensor algebra particularly in my playlist Mathematical Physics. But I have not provided videos on tensor calculus in that playlist. But it will be needed in the study of general theory of relativity. So, in this playlist of general relativity, I will also provide the important lectures on tensor analysis. Okay, I will introduce you some of the important tensors and particular the tensor methods of tensor calculus in this playlist, okay, apart from the concept of general relativity, okay. But I will suggest you, before watching the videos on this general relativity, you must watch or you must study tensor calculus, okay, because when you will have a concrete knowledge of tensor calculus, then it will be very easier to understand the concept of general relativity, okay. Basically, this general relativity is named after Albert Einstein, who proposed first of all this theory, but after that there are so many mathematicians who developed this general relativity. And in our course of lectures, we will see the contribution of different mathematicians in the field of general relativity. In fact, you know, there are actually two fundamental theories in physics, okay, which are of great importance, particularly in studying the behavior of matter. And actually, before this theory, the physics was known as classical physics. So, you can say that in classical physics, there are two fundamental theories to discuss the behavior of matter. The first one is known as Newtonian Theory of Gravitation, and another is electrodynamics, or you can say classical electrodynamics. As the name says, if you are talking about Newtonian Theory of Gravitation, this was proposed by Sir Isaac Newton. And the electrodynamics, this is actually based on the Maxwell's fourth field equations, okay. Actually, these two theories are of great importance in classical physics. In fact, when you talk about Newtonian theory of gravitation, definitely you have studied it in your lower classes. And you know, in Newtonian theory of gravitation, it is said that gravitational interaction is due to mass. Mass is the cause of gravitational interaction, okay. According to Newton's law of universal gravitation, you know, if there are 2 point masses m1 and m2 separated by a distance, let us say r, then this point mass m1 attracts m2 towards it by a force F. But this is just an action. And according to Newton's third law of motion, then m2 will also exert the same force F, but in opposite direction, that is towards m2. So this gravitational force is an attractive force, and this is caused by mass in accordance with Newtonian theory. And you know, according to the universal law of gravitation proposed by Newton, this gravitational force is given by g times m1 m2 over r square when r is greater than 0. It means when the two masses will be in contact, r is 0, then according to this formula you can say F will actually undefined. So this is r equal to 0 is called the singularity of this law. So definitely this formula will be valid when you take r greater than 0. So in a statement of Newton's law of gravitation, it is said that 2 point masses separated by a finite distance, okay, and also when r will tend to infinity, then F will tend to 0, okay. So the distance between two masses should be not 0, and it should be not infinite, because when separation will be infinite, this force will be not experienced, and when separation is 0, this law will be unable to find the force. It does not mean that force is not acting between the two masses. force is acting. But Newton's law of gravitation cannot find gravitational force between two masses which are in contact. Okay? According to this law, in that condition, the force becomes undefined. Okay? I have put here this minus sign. This minus sign, this is due to the attractive nature of this gravitational force. So according to Newtonian theory of gravitation, one point mass interact another point mass. Okay? And so this is just a action at a point concept. Okay? So in nutshell, you can say, according to Newton's theory, mass is the cause of gravitational force. Okay? So, if a particle or a body is massless, it cannot be attracted gravitationally, or it cannot exert a gravitational force on another mass. Okay? In accordance with Newton's theory, cause of gravitation is mass, as Newton's gravitation theory says. But when you will study general relativity, then you will see that Einstein has changed this idea. Cause of gravitation in accordance with Einstein theory is not mass. This is actually the curvature of a space-time. We will see later on. Okay? Now, the another fundamental theory which actually deals with the behavior of matter, that is the electrodynamics. In fact, electrodynamics deals with the behavior of charged matter, okay, in the presence of electromagnetic field. When you place a charged particle or a charged body either at rest or in motion, in an electromagnetic field, it experiences electromagnetic forces. Okay? And this theory deals with the behavior of charged particle or charged body or charged matter, you can say, particularly in electromagnetic field. Okay? When I have talked about a special theory of relativity in my playlist which is named Special Relativity, you can see that in those videos I have definitely talked about how this special relativity was originated, why Einstein has proposed a special relativity. Actually, you have seen that Maxwell's field equations are not invariant under the classical Galilean transformation. And therefore, Einstein pointed out that if the laws of physics should be invariant under the particular transformation of frame, then definitely laws of electrodynamics, or you can say the Maxwell's field equations, must be invariant. But it was found that Maxwell's field equations are not invariant under the Galilean transformation. But these are invariant under the Lorentz transformation. Okay? So actually, a special theory of relativity had its origin in the development of electrodynamics. Okay? On the other hand, when you will talk about general theory of relativity, then you will see that this general theory of relativity is nothing. This is simply the relativistic theory of gravitation. Okay? So, a special theory of relativity was originated in the development of electrodynamics. When electrodynamics was developed, then Einstein needed the development of a special relativity, and he proposed this theory. But when Einstein tried to explain the gravity, then he found, or he realized, that there must be a theory which actually correctly explains the gravity. And that theory is known as general theory of relativity. So actually, general theory of relativity is concerned with theory of gravitation. So you can say this is just the modification of Newtonian theory of gravitation. Okay, Newtonian theory of gravitation. Okay. In fact, the special theory of relativity only accounts for inertial systems, in the region of free space, where the gravitational effects can be neglected. Okay? Actually, in those systems, the law of inertia holds good and the physical laws retain the same form. All these facts we have studied in the course on special relativity. If you have not watched my video on special relativity, I will again suggest you go through all those videos. These facts you will find there. Okay. So as you know, this special theory of relativity is concerned with inertial frame of reference. It is valid, it holds only in inertial frame of reference. Therefore, the name is special. It does not hold in non-inertial frame or accelerated system. Okay? So you can say that a special theory of relativity does not account for non-inertial or accelerated system. Because what are non-inertial systems or non-inertial frames? They are accelerated frames. That is, those frames in which law of inertia does not hold. Okay? So, I have written here that the special theory of relativity does not account for the non-inertial system or the accelerated system. For example, there is a famous phenomenon which is called clock paradox. Okay? And another is the universal phenomenon of gravitation. Actually, these two phenomena could not be accounted by a special theory of relativity. If you will try to explain the clock paradox or the universal universal phenomenon of gravitation, you will be not able to explain these two important phenomena on the basis of a special theory of relativity. Thus, naturally, we wish to extend the principle of relativity in such a way that it may hold even for non-inertial systems. Okay? And consequently, the extended theory may explain the non-inertial phenomenon like clock paradox and particularly the phenomenon of gravitation. Okay? So we must extend this theory. Actually, the extended theory is known as General Theory of Relativity. This extended theory is called General Theory of Relativity. In fact, in developing the General Theory of Relativity, it is helpful to analyze the predictions of a special theory of relativity with respect to the phenomenon of gravitation. Okay? On the generalization of a special theory of relativity with respect to gravitational phenomenon, the theoretical prediction led to a small deviation from the observed phenomenon in the following cases. You will see or now. In fact, as I have told you that when we talk about the development of general theory of relativity, then you will see that this theory is very helpful to analyze the predictions of a special theory of relativity with respect to the phenomenon of gravitation. Okay? And so on the generalization of a special theory of relativity with respect to gravitational phenomenon, the theoretical predictions led to a small deviations from the observed phenomenon, in particularly in some cases which I will now discuss. So what is observed? In fact, there are some very important natural phenomena when we will try to explain those phenomena on the basis of a special theory of relativity, then the result obtained is not exactly same as it is seen in the observation. So the theoretical value obtained on the basis of a special theory of relativity of gravitation does not agree with the observed value or the practical value. So I am going to mention three very important phenomena where you will see that the observed value will deviate from the predicted value, that is value predicted by a special theory of relativity. Okay. In first example, we are going to take a very important phenomena which is called advance of perihelion of planets. Okay. In fact, the special theory of relativity of gravitation leads to the phenomenon of perihelion of planets. But the precession of a planet observed that accounted by a special theory of relativity are not in the same amounts. It means the result obtained from the special theory of relativity and the observed value do not agree with one another. You can take an example for this purpose. If you talk about the planet Mercury, okay? Actually, in accordance with a special theory of relativity, in case of planet Mercury, the retardation of the perihelion is at the rate of 7.2 seconds of arc per century. But if you will talk about the observed value, this is actually the theoretical value which is predicted by a special theory of relativity. But the observation says that the perihelion of Mercury advances at the rate of 43 seconds of arc per century. So the theoretical value, that is the value obtained from a special theory of relativity of gravitation, and the actual value, or you can say the observed or experimental value, differs much. You can see. You can see actually here that the effect observed is almost 6 times greater in magnitude as accounted by the special theory of relativity. So we can say that our special theory of relativity of gravitation fails to explain the phenomenon of advance of perihelion of planets, because the predicted value by this theory and the actual value observed in practice are not equal. There is a large difference between these two values. Okay. So in this way, we can say that the phenomenon related to gravitation cannot be successfully explained by the use of a special theory of relativity. Okay. Now, I will talk about another very important phenomenon that cannot be accounted by a special theory of relativity. And this is regarding the shift in spectral lines. In fact, the spectral lines emitted by atoms, even in a very powerful gravitational field, when it is when shift in this spectral line is explained on the basis of a special theory of relativity, then in accordance with this theory, there will be no shift in the spectral lines emitted by the atoms even in a strong gravitational field. There will be no shift. Okay? But observation says, it is found in practice, that there is a shift of spectral lines towards the red end. that is toward the longer wavelength. So you can say that shift in spectral lines in a gravitational field cannot be explained on the basis of a special theory of relativity. Because in accordance with a special theory of relativity, there will be no shift in spectral lines emitted by the atoms even in a very powerful, very strong gravitational field. But our actual observation says that there is a shift of a spectral line towards the longer wavelength side, that is toward the red end. Okay? So, regarding this shift in spectral lines, this special theory is unable to explain it. Okay? Now, we will talk about the third phenomena, which is actually a very important phenomenon. And we will talk about this phenomenon separately when I will start to discuss the different concepts. This is just introductory lecture. Okay? And this is regarding deflection of light rays due to the gravitational field. Deflection of light rays due to the gravitational field. Actually, the special theory of relativity predicts that when the light rays passes close to the sun, okay, they are deflected by an amount 0.88 second of an arc. Okay? When light rays passes close to the sun, there will be a deflection of light rays, and the value of deflection is 0.88 second of an arc. Okay? This is the prediction of a special theory of relativity. If one try to calculate the deviation of light rays when it passes close to the sun on the basis of a special theory of relativity, then it is found that this should be equal to 0.88 second of an arc. But is it the correct value? Answer is no. Our observation says when actually practically this deviation is measured, it is found that this deviation is not 0.88 second, but it is 1.75 second of an arc. Okay? So you can see the observed value is almost 2 times of the value predicted by the special theory of relativity. So, a special theory of relativity also does not give correct prediction for the deflection of light rays due to gravitational field. Okay? So, in this way, you can say that these are some important phenomena where a special theory of relativity does not agree, or the results obtained from the special theory of relativity do not agree with the observed value. And that's why people needed some new theory which will predict the values which will be close to the observed value. Okay? So you can say that the special theory of relativity, due to these deviations from observations, may not be considered wrong, since for long velocities it reduces to Newtonian theory, which is valid to a high degree of accuracy. Flatly you cannot refuse, you cannot say, give a flat statement that a special theory of relativity is wrong. It is not wrong. Because when we talk about the very small velocity, in fact in that condition you will see that the results of a special relativity is transformed into the results of Newtonian mechanics. And Newtonian mechanics, you know, is very accurate at low speed. Okay? So at low speed, since the results of a special relativity agrees with the results of Newtonian physics, so you can't say that this theory is wrong. Okay? there will be some fault, there should be some modification so that it may account for the gravitational phenomena. The original special theory of relativity is so designed that it is unable to explain the gravitational phenomena. Okay? So you can say the special theory of relativity of gravitation seems to be slightly wrong, not completely wrong, for the phenomenon in which velocity approaches to the velocity of light, because it could not account the correct amount of bending of light rays towards the sun. And also this theory of gravitation seems to fail for fixed particles in gravitational fields, because it could not predict the redshift of spectral lines emitted by the atoms even in powerful gravitational fields. Okay? So this special theory of relativity also seems to be wrong for the phenomenon when velocity and gravitational field both are present, since it could not predict correctly the precision of perihelion of planets, which is considered to be due to their velocity and the strength of gravitational field. Okay? So these are the shortcomings of a special theory of relativity. So after this discussion, it is obvious now that the Minkowski space-time continuum does not account the natural phenomenon of gravitation. Okay? And therefore, we have to modify Minkowski space-time continuum. Okay? In fact, this is also due to the fact that general theory of relativity, when you talk about general theory of relativity, you will see, we will consider that the motion in gravitational field is some type of inertial motion, as accelerating the passengers relative to a suddenly stopped carriage. Okay? The acceleration is due to Newton's law of inertia, according to which a body at rest, remains always at rest, and a body in motion moves with the same velocity till no external force is applied. Okay? Actually, this also explains why the acceleration due to action of gravity is independent of the mass of the body. We will actually explain this fact later on in very detail. And as the force of gravitation is zero at infinite distance, we have seen in accordance with Newtonian theory, from the mass or at the attracting bodies. Therefore, it is assumed that a space close to the attracting bodies or the mass does not follow the Minkowski space-time continuum. Okay? Hence, for accounting the observed fact of gravitation, we have to modify Minkowski space-time continuum. Okay? Minkowski space-time continuum. In fact, the observations of gravitational redshift on Earth support this modification of Minkowski space-time. Okay? I have already discussed the Minkowski space-time in my playlist on special theory of relativity, and you can see there the idea of the space-time. In fact, when you talk about Minkowski space-time continuum, then the line element, which is also called a space-time, denoted by this symbol ds square, that is given by ds square equal to minus dx square minus dy square minus dz square plus c square dt square. C, this is velocity of light in free space. Or it is also written as ds square equal to dx square plus dy square plus dz square minus c square dt square. You may write. Okay. So this is the expression for the line element in Minkowski space-time continuum. Now, in tensor form, when we write this equation 1, then its tensorial form is written as ds square equal to g mu nu dx nu mu dx nu. This is the tensorial form of this equation 1. Okay. Here, this g mu nu is called metric tensor. This is called metric tensor. In fact, this equation 2 is the general result for the line element. And you can obtain this result defined in equation 1 in some particular situation or particular case. Okay. So you can, if this equation 1 is derivable from this general result, then you can say that in the region which is far from gravitational field, then general theory of relativity reduces to the special theory of relativity. It means if you are not talking a space where gravity exists, then a special theory of relativity is all right. Okay? And if there is a source of gravity and you find the gravitational effect of that source at a very large distance, at infinite distance, then there will be no gravitational effect there. And so, in those regions which is infinitely distant from the source of gravity, a general theory of relativity will be just converted into the special theory of relativity. Okay? And so you can say that this Minkowski space-time continuum holds in region far from gravitational field. It means this holds in free space where gravity does not exist. But if you have to take this gravity under account, definitely this Minkowski space-time continuum will not hold. Okay? In fact, in this equation 2, this metric tensor G mu nu, I have already discussed metric tensor in my previous videos and you can watch this. Actually, this metric element denoted by G mu nu, this is a second order tensor, you can see. This actually represents that the space is not flat but it is curved. So we simply say that this represents a curved geometry. And so according to general theory of relativity, a space is curved in a gravitational field. Mark this. According to general theory of relativity, our space in gravitational field is curved, not flat. Okay? And since a space is curved in gravitational field, therefore, the geometry of a space in a gravitational field cannot be Euclidean, but it will be Riemannian. Its geometry will be Riemannian because the idea was originally developed by a great mathematician, Riemann. Okay? So you can say that free motion in gravitational field or in a non-Euclidean field, a non-Euclidean space is not rectilinear, not straight, but it will be curvilinear. In lower classes, you study that when a particle is dropped in a gravitational field, it follows a rectilinear path. Okay? But actually, when we will talk about this problem in terms of the general theory of relativity, then you have to say that actually in general the path followed by that particle moving freely in this gravitational field will be in general a curvilinear path, not a straight path. But if we consider let us say this is a curvilinear path, but if you consider a very small element of this curvilinear path, What will be that element? That will be definitely a straight line, because a very small element of any curve will be straight. Okay? So if we consider a very small element of a curve, it will nearly a straight line. Okay? Definitely you have. And therefore, it is very difficult to distinguish the gravitational and the inertial forces in a small region of space. It is very difficult. In such regions, a non-inertial coordinate system is equivalent to inertial system. Okay? In which an additional gravitational field operates with the same acceleration of falling bodies, which is due to inertial forces in the non-inertial system. Now, since classically the difference between the inertial and non-inertial system is merely that in the latter the inertial forces come into play. Okay? Hence, you can say the theory of gravitation also deals with the non-inertial system, unlike the special theory of relativity, which deals only with inertial system. I have told you it in the very beginning of my lecture. The general theory of relativity deals with the system deals with the non-inertial system, but special relativity deals with inertial system. Okay, this is the basic difference, and that's why it is said that this is the region. The theory of gravitation is also called general theory of relativity. So finally you can say this general theory of relativity is what? This is theory of gravitation proposed initially by Albert Einstein, modifying the Newtonian theory of gravitation, and after his general theory of relativity, there are so many workers, so many mathematicians who has developed this theory of gravitation, which is called general theory of relativity. Okay? So this was just a brief introduction regarding this general theory of relativity. But after this introduction, I will provide the basic concept of this general theory of relativity along with the ideas of tensor calculus. Okay? Thank you very much.